Hi everyone. In this video, we'll be using integration to find volumes of three-dimensional solids. In particular, we will practice visualization of three-dimensional solids. We will use technology to visualize those three-dimensional solids. And then we'll extend ideas from finding areas of planar regions to three-dimensional solids via integration. So to start with, in general, finding the volume of some three-dimensional figure can be a very hard problem. If you sort of imagine like the most generic possible three-dimensional solid, right? You could have things, right? These are three-dimensional. So you could have three-dimensional objects, right, which are sort of very strangely shaped. And you're not going to have very nice formulas for finding the volumes of those kinds of solids. But in this video, we're going to restrict ourselves to a specific case of three-dimensional solids, a particular type. And these are going to be ones where cross-sections perpendicular or parallel to a particular axis are a consistent shape and have some area that we can easily compute. To get started on this, let's actually first head over to Desmos to get a little visualization of the kinds of three-dimensional solids we're talking about and to see how we can use integration to help find the volumes of these solids. So the kinds of three-dimensional solids, again, that we want to deal with are ones where if we take cross-sections, in this case, you can see my XY plane is sort of sitting down here. And I want to imagine that if I take cross-sections that are parallel to the x-axis or perpendicular to the y-axis. So I'm just imagining sort of coming through and chopping my function like this. I get cross-sections that are a consistent shape. So in order to see this, let's actually come over here. I've actually got some of the cross-sections plotted here. So hopefully you can see here, as I come here, if I change this value of A, you can hopefully sort of see that all of the cross sections here are in fact semicircles. Now, semicircles are nice shapes. I know how to find the area of half of a circle, right? So because I can find the area of any one of these cross sections, I can actually find the volume of this entire solid simply by integrating across all the relevant y values to get integrating the cross-sectional areas to get the total volume. Okay. To see this in a little more detail, let's actually turn this off for a moment. So again, you want to sort of imagine that you can find the cross-sectional area. In this case, that would be A of y. Okay. And so if you think of sort of a slice here, if I come in and take sort of a slice out of this, in this case, each of my slices is going to look something like a semicircle, but you can sort of imagine maybe it's been we sort of thicken it a bit. So you come over here, you're actually going to take a little slice sort of dy, and then you can find here the area of this. So since it's a semicircle, it would be 1/2 pi r squared. We'll actually compute for this particular surface, or this particular solid, we'll compute this a bit later. But just in general, right, if I can find this area, and then I sort of thicken it out by dy, and then if I want to find the total volume, then I would simply add all of those up over some range of y values. And so in this case, I would get something that looks like this. Okay. So again, we can do this for any general surface solid, as long as we can find these cross-sectional areas. Now, practically speaking, that means the cross-sectional areas need to be nice shapes. Primarily, we're going to be looking at things like potentially triangles or squares or semicircles, right? There needs to be something we can easily find this cross-sectional area of. But in general, if you can find that cross-sectional area for any of those slices, then you simply integrate those over the range of relevant y values to get your total area. All right, let's now switch back over to the slides to sort of summarize then this main idea before we proceed to look at some specific examples. So in summary, if for each S value in some interval AB, I can find this cross-sectional area A of S, And if it is continuous across that interval, then the volume of the solid is found simply by integrating the range of cross-sectional areas from A to B, whatever that range happens to be. Let's see how this works in a particular example. So imagine that you're asked to find the volume of the solid whose base is the region bounded between y is equal to x squared and y is equal to 4, and whose cross sections perpendicular to the y-axis are semicircles. As we begin to think about problems like this, we need to think about the geometry of the situation. So the first thing we want to think about is the base. So the base is the region bounded between y is equal to x squared and y is equal to 4. Okay. We're thinking about something which has a base that looks like this. And we also know that cross sections perpendicular to the y-axis, so those are cross sections in this direction, are semicircles. So again, if I think about sort of what this looks like, if I sort of think about raising this up out of the plane, right, what ought to happen is I would have semicircles popping up like sort of at each one of these lines. This is the base of some semicircle, okay? Now, it's very hard, even with almost a decade of practice now, it's very hard to draw these sorts of figures. I'll try to give it an attempt to give you some idea of what's going on here, but again, these are difficult to draw. So I'm going to imagine here is my XY plane. Okay. This direction is where I'm going to lift up sort of those semicircles. So if I just think about this graph, this lying in this XY plane, which I'm sort of imagining, coming out of the board here, this is going to look, something like this. Okay. And then again, it's bounded by this. So here is that base. Okay. That base is again lying in this horizontal plane here. And now out of each of these is going to come a semicircle. So you can sort of imagine that there's going to be a semicircle, here on the end. And then those semicircles are going to be sort of getting smaller and smaller and smaller. So you can sort of imagine a shape that looks something sort of like this. Now, again, that's a very rough estimate. In fact, to help us visualize it, let's actually flip over to Desmos. This is, in fact, exactly that shape that I showed you earlier. All right, now let's flip back over to Desmos. So let me start here just in the XY plane. Again, this is just my base here, right? So this is the region bounded below by y is equal to x squared, and above here by y is equal to 4, okay? And again, now what I want to do is I want to sort of imagine thickening this out and creating all the cross sections that are semicircles, okay? So here now, if I rotate this to sort of a three-dimensional shape, you should be able to see there's sort of what that figure ought to look like. And here's sort of roughly the perspective from which I was trying to sketch it earlier. All right. Now, what I'd really like to do is I would like to find the volume of this. So to do this, I need to find the cross-sectional areas, okay? And then once I have those, I'll integrate those over the relevant range of values. So let's start by thinking about the cross-sectional areas here. So in fact, let me come here and actually turn off a bit of this. So if you think about, again, those cross sections, you can hopefully see here, they all sort of look like semicircles. So even as I slide this oops, my graph is moving. So even as I move this A value here, right, this is just moving that cross section. You can see those are all semicircles. Okay, so the first thing I'm going to want to think about is sort of how can I write an expression for the area of that cross section. Now I'm going to call this sort of the area of the slice we're going to take out of here. Now, it is a semicircle. Okay. So the area of half of a circle, area of a circle is pi r squared. So the area of the semicircle should be 1/2 pi r squared. And now, of course, the question is, well, what is this radius? Okay. Well, this is where it may be helpful to actually go back to the plane view. Okay, so if I come here, okay, if I come back over here, this radius is really going to be the distance from the y-axis here to the outside portion of the graph here, right? So it's really the distance from x is equal to 0, from the y-axis, to this curve, x is equal to, sorry, y is equal to x squared. Okay, so if I come off to the side here for a second and just sort of think about that piece of the graph, right? So I really want to know for an arbitrary y value here, right? Let's see, this x value, well, this curve is y is equal to x squared. So if I solve that, that's x is equal to square root of y. And so this distance at some height y, this distance here is simply square root of y. That's going to be my radius. So the area of this slice is 1/2 pi times the square root of y squared. Okay. Written another way or simplified, that is 1/2 pi times y. Okay. That now gives us, for any particular y value that we happen to be at, that gives us the area of the cross-sectional slice. So now if we switch back over here, and we're looking in this perspective, and we're wanting to know what's the area of this sort of semicircle that's highlighted here, it will be 1/2 pi times whatever particular y value you're looking at. In this case, that's what this A slider gives you. But now I want to actually add up all of those slices to get the total volume. Okay, so in this case, if I want to find the volume, okay, then the volume, total volume, ought to be the integral of 1/2 pi y dy. Okay, so since all of my slices are perpendicular to the y-axis, I'm integrating with respect to y, right? Each of those, I'm ranging over my slices in the direction of y. And now I just need to know, well, what do they range from? Again, these are what y values do they range from? And again, if I switch back to this sort of 2D view, right, my y values are ranging from 0 up to 4. So I ought to integrate from 0 to 4. And so now this integral, I can pull the 1/2 pi outside. The antiderivative of y is y squared over 2. I'll evaluate at 4 and 0 and take a difference. At 0, this is just 0, and evaluated at 4, let's see, I'll get 4 squared, which is 16, but divided by 2 and 2 again, so 16 divided by 4 is 4. I should get 4 pi as the total volume here. Okay. And so this figure, which maybe originally was a little difficult to make sense of, we can actually find its total volume. It is 4 pi. We again find that first by finding the cross-sectional areas of these slices. Each of those cross-sectional areas was 1/2 pi times y. And then we find the total volume by simply adding up all of those, or integrating all of those cross-sectional areas, right? So we add up 1/2 pi y for y values ranging from 0 to 4. This is now just a definite integral. It's a fairly simple definite integral. We compute it and we get 4 pi, which is our total volume here. All right. Let's look at another problem. And to do this, we'll switch back over to the slides. So now let's imagine we're asked to find the volume of the solid whose base is the region bounded between y is equal to 1/8 x squared and y is equal to square root of x, and whose cross sections parallel to the y-axis are squares. Again, we can do a lot of this by hand, okay, but we'll visualize it with technology in a bit. So I first want to start by thinking about my base, okay? So my base is bounded between this function 1/8 x squared and y is equal to the square root of x. So this is my base sitting here. And the first thing I'm probably going to need to know is sort of what are the bounds on my base here, right? So clearly this corner is 0, 0. To find this upper limit of integration, you might just be able to sort of observe here that this intersection, these values will be the same when x is equal to 4. So 4 squared would give you 16 times an eighth would give you 2. Square root of 4 is 2, so they clearly intersect there. And then a height of 2, so this intersection is 4, 2. If you wanted to solve that exactly, right, you could set 1/8 x squared equal to the square root of x. If you square both sides, subtract, factor, you'll get a factor of x minus 4, which will give you that intersection. But we can sort of quickly find the bounds on this this base. Now, in terms of cross sections, right, we're told that our cross sections parallel to the y-axis, so that's cross sections in this direction. Notice it would be the same if I said perpendicular to the x-axis, right? So there's sort of two ways to say the same thing. But if I take these cross sections parallel to the y-axis, they are squares. Okay, so in this case, right, if I sort of imagine breaking this out, right, I'm going to get this shape that has this sort of base like this, but then it has sort of squares for sides. Let me see if I can sort of do this. So you get these sides coming up like this, so that every one of your cross sections that you cut here are in fact little sort of squares. Okay? That's not a great picture, so we'll use Desmos to help us visualize this. Now, again, here we start by looking at the plot of our base. So this is just that same region we plotted before. Again, you can see that the base starts sort of here at 0, 0 and goes over here to 4, 2. And now we want to think about, again, building up that surface. So if I come over here, I can sort of turn on the solid piece of it. And now if I go to the three-dimensional view, you'll get a much better look at what this solid looks like. Okay, sort of drag it around so you can see what it looks like a bit there. And now I can also turn on the cross section so you can get a good look at what's going on there, right? So you can hopefully sort of see here that if I come and I move this plane, right, we're just cutting cross sections parallel to the y-axis, right? You can see hopefully that all of those intersections are squares, no matter sort of how I cut that there. All right, so what we want to think about then is we want to find the area of one of these cross-sectional slices. And then once we have the area of those cross-sectional slices, then we will add them all up or integrate them. Now, again, notice here, the area of your cross-sections changes as you change, in this case, your x, right? So again, as this x changes, and again, we can go back to the 2D view, right? As this x value changes, right, the width of my cross section is also going to change. Okay, so my cross sectional area is going to depend on x. All right, but each of these cross sections is just a square. Okay, so what is the area of one of my slices? Well, it's a square, so it's just going to have area side squared. Okay, but what is the side? Well, again, let's go back to this 2D view. Okay, so the area of the side is just going to be the length of this little line segment here, okay, which is just the difference between this upper function's y value and this lower function's y value. Well, this upper function here, right, this function is y is equal to the square root of x. This lower function down here, that's the y is equal to 1/8 x squared. Okay, and so the height, the difference between them will just be the difference between these two functions. So back over here, this is really just square root of x minus 1/8 x squared to get the area of my slice. All right, again, notice the area does depend on x. So now to find my total volume, right, I'm going to integrate each of those slices. So I'm going to integrate that. For x values, my x values over this region range from 0 to 4. Okay. Now, in order to calculate this, the first thing I'm going to do is I'm going to just expand the integrand here. So if I square this, I will get x, I'll get minus 1/8 x squared times square root of x. So that's x squared times x to the 1/2, or x to the 4/2 times x to the 1/2. So I get a minus 1/8 x to the 5/2, and then another minus 1/8 x to the 5/2. That'll give me minus 1/4 x to the 5/2. And then I will get a plus 1/64 x to the 4. My dx is right on the edge there, but hopefully you can see it. But now I'll take an antiderivative and evaluate at the endpoint. So my antiderivative will be x squared over 2. I'll get a minus 1/14 x to the 7/2. And I'll get a plus 1 over 320 times x to the 5th. And that's my antiderivative. And then that'll be evaluated at 4 and 0 and take a difference. Okay. Now, if I plug in 0, all of these terms have an x. That goes away. When I plug in 4 and do the subtraction, and I'll let you sort of, you can work that out on your own if you want. But you could just plug in 4 here, right? So you'd get 16 over 2 minus 1 over 14, 4 to the 7/2. That's the same as the square root of 4 to the 7th. So that's 2 to the 7th. So you have to figure out what that is. And you have to figure out 4 to the 5th. It gets sort of tedious. But you plug this in a calculator, and you get that the final answer is 72/35, which is approximately 2.05. Okay. Now, what the really important step here for me, right, is getting this volume set up. In fact, it'll be quite common that I may ask you on a homework or a quiz or a test simply to set up the integral for the volume, because once we have the integral for the volume, there are any number of tools at our disposal to either calculate this integral for us or approximate it. But the real key here is appropriately setting up the integral that gives us the volume. But again, it's nice to have a final answer. Our final answer here to 2 decimal places is about 2.05. Again, what did we do? We found the area of one of those cross-sectional slices. We then integrated the areas of those cross-sectional slices over the entire range of x variables. That gave us our final answer. I want to go back to the slides for a moment. And I want us to take a look at one more example, but this time I want us to see that we can actually do this without being able to fully and perfectly visualize any of these shapes, okay? So imagine you're asked to find the volume of the solid whose base is a circle of radius 2 and whose cross sections made perpendicular to the x-axis are squares. All right, so again, as we've done before, we'll want to start by visualizing our base. Okay. And again, it's just a circle of radius 2. I guess I didn't say it here. I intend for that to be centered at the origin. Okay. And so I could actually, even though I didn't sort of give you an equation for this, the equation of this circle is just x squared plus y squared is equal to 4. So in general, the radius of the circle, or it's x squared plus y squared, is equal to radius squared. So the circle of radius 2 has a 4 over here. And now we know that the cross sections that are made perpendicular to the x-axis are squares. So cross sections made in this direction are squares. Okay. Now, my point here, right, is that I can still figure out the area of one of these slices, right? If I just think about the fact that this should be a square and I have its base essentially here. I'm looking at sort of a flattened version, and here's the base of the square. So if I want to figure out the area of that square that has this as its base, I just need this length. Okay. Now, in order to do this, I actually need to figure out like what's the y value here and what's the y value here. So I'm going to take this equation of the circle and I'm going to solve this. So y squared is 4 minus x squared. That gives me that y is plus or minus the square root of 4 minus x squared. Now, the plus solution actually gives me the top half of the circle. The minus solution gives me the bottom half of the circle. So if this is some x value, then this y value is positive square root of 4 minus x squared. And this y value is negative square root of 4 minus x squared. And so to find the length of this side, it's just going to be the top x value minus the bottom x value. And so what you see is you get 2 times the square root of 4 minus x squared to be this length here. Now, that's going to be my side length that I'm going to use to find the area of this slice. So the area of one of these cross-sectional slices perpendicular to the x-axis is going to be 2 square root of 4 minus x squared whole quantity squared, which simplifies to 4 times 4 minus x squared. Okay. And now, in order to find the total area of the region, or sorry, the total volume, right, I can now express the volume as the integral of 4 times 4 minus x squared dx, where my x values are going to range from what? Well, over here on the circle is minus 2. Over here on the circle is positive 2. We're going to integrate from minus 2 to 2. Okay. And so now we simply need to compute this integral. So we can pull the 4 outside of the integral. I'll do that first. Pull this 4 outside. And let's see. Now, taking this is a fairly simple antiderivative. So this is 4 times, this will be 4x minus x cubed over 3. I'm going to evaluate at 2 and negative 2 and take the difference. And so what will this give me? This will give me, when I evaluate at 2, that'll give me 4 times 2, which is 8, minus 2 cubed over 3, so that's 8 thirds. That's everything evaluated at 2. Minus, when I evaluate at negative 2, I'll get 4 times negative 8 minus negative 8 over 3. Now this minus negative 8 thirds That can become a plus. Okay. And let's see what happens if I distribute this. What do I get? I get 32. I get minus 32 thirds. Now I have minus 4 times negative 8, so that's plus another 32. And I get minus another 32 thirds. So I end up with 32 plus 32 is 64 minus 64 thirds. And let's see, what is this? This is actually the same as I can factor out a, if I factor out a 1/3, this is really 1 times 64 minus 1/3 times 64. So this is 2/3 times 64. And so that's 128 thirds. Okay. And so I can find the total volume of this solid. It is 128 thirds. Okay. Now, again, here I didn't need to do sort of all the fancy visualization, although that is really nice to help get a conceptual understanding of what's going on. But I really don't have to do all that visualization if I understand the process, right? I need to find the area of one of the cross-sectional slices. And the way I did that, in this case, since they were squares, was to find a side. I can find the side length just by working in the plane here. I don't have to work in 3 dimensions. Then I know that the area of that 3-dimensional slice will be that side length squared, but I can compute that. And then I simply integrate each of those cross-sectional slice areas to get the total volume of the figure. So now that we've worked a number of examples together, I think it's time for a knowledge check. And I want you to see if you can work out on your own one of these volume problems by slicing. So let's take a look at one more problem. So I want you to find the volume of the solid whose base is the region formed by x is equal to 0, y is equal to 1/2 square root of x, and y is equal to 1, and whose cross sections perpendicular to the x-axis are semicircles. So remember the process. First, draw a sketch of the base of the solid. Then see if you can use that information to find the areas of the cross-sectional slices. Then integrate those cross-sectional slices over an appropriate range of x or y values. Okay, great. Let's see how you did. So first, we want to sketch the base. So if I look at this, this is bounded by, well, x is equal to 0 is just the y-axis. Y is equal to 1/2 square root of x. And y is equal to 1. Okay. So my base region here looks something like this. Okay. Now, my goal is going to be to find the area of one of the cross-sectional slices. Okay. And so if I think about these slices, what does it tell me? The cross-sections perpendicular to the x-axis, so cross-sections like this, are semicircles. Well, to find the area of a semicircle, that's 1/2 pi r squared. And so what I need to do is I need to think about, well, what's the radius going to be? Now, keep in mind, this base, if I think about the semicircle that's going to pop up out of here, that pink base is actually going to be twice my radius, right? Because it's going to be the radius of a, sorry, it's going to be actually the diameter of a semicircle, right? And so what I want to do actually is I want to find this distance, but then to get my radius, I just want to take half of that, okay? So if I look at this distance here, well, this distance is just upper y value minus lower y value. So this distance in pink here is simply 1 minus 1/2 square root of x. Okay. Now, again, that's my diameter. My diameter is 1 minus 1/2 square root of x. And so my radius is 1/2 of that. So it's 1/2, 1 minus 1/2 square root x. Okay. Now let me plug that in over here to my formula for the area of my slice. So my area of my slice is 1/2 times pi times my radius, which is 1/2, 1 minus 1/2 root x, quantity squared. Now I can do some algebraic simplification here. I square the 1/2, that becomes a 1/4. I'm going to multiply by this other 1/2, that's going to become a 1/8. I'll get a pi, and then I'll have a 1 minus 1/2 square root of x squared still. Okay, now I'm going to square this piece. So I'll get 1/8 pi. Now I'm going to square this by foiling it. I'll get a 1 times 1, which is a 1. I'll get a minus 1/2 square root of x and a minus 1/2 square root of x. That'll just be a minus square root of x. And then I'll get a minus 1/2 square root of x times minus 1/2 square root of x. That'll be plus 1/4. Square root of x times square root of x is just x. Okay. So there's a formula for the area of my slice. I'm going to give myself just a little more room. I'm going to erase my sketch here. You may on the video want to come back to it at the end when we talk about some bounds. Okay. So now if I want to find the total volume, the volume should be the integral of these slices okay. And I now need to figure out the appropriate range of x values. And that's where I said you may on the video want to drag back and look at what those bounds should be. So because of the way we have it set up, we're looking at the range of x values. X starts at 0. And then the upper point is actually where these two curves, where y is equal to 1/2 square root of x and y is equal to 1 intersect. They intersect when x is equal to 4. We're going to integrate from 0 up to 4. And so what will that be? Well, we can pull out a 1/8 pi. That's just a constant we can pull outside of our integral. And now we'll take the antiderivative of the rest of this. So the antiderivative of 1 is just x. The antiderivative of square root of x, well, that's really what? That's really x to the 1/2. I increase the power, x to the 3/2, and divide by 3/2. So that's going to be minus, dividing by 3/2 is the same as multiplying by 2/3, x to the 3/2. Plus, now the 1/4 can hang out, x, I'll increase the power by 1, divide by the new power, so x squared over 2, but it's times 1/4, so it's x squared over 8. And now I'm going to evaluate that at 4 and 0 and take a difference. So I have 1/8 pi. When I evaluate all of this at 0, everything will be 0 and it'll go away. So it's really just when I evaluate at 4 that things matter here. So I'll get a 4 minus a 2/3, 4 to the 3/2, plus a 4 squared, which is 16 over 8. Okay. Now simplifying a bit more, I'll get 1/8 pi times, this will be 4 minus 2/3 times, all right, 4 to the 3/2. So we take a square root of 4, that gives us 2, and then we cube that. So that's going to give me an 8 plus a 16 over 8. Okay. Now what I can sort of see is that I'm going to need a common denominator. I have a denominator here of 3 and a denominator there of 8. Let me go ahead and clean this up a bit. This, I can replace this 8 times 2/3. That's really 16/3. Okay. I can get a common denominator of 24. Okay. And so when I do that, actually, sorry, I can make this a little easier, right? I have 16 over 8, right? That's just 2. The advantages of simplifying things first. So that's just 2. And now I can put everything in terms of thirds. So this is 1/8 pi times, this will be well, 4 plus 2 is 6. In terms of thirds, that's 18 thirds minus 16 thirds. And so we get, that's 2 thirds. So 2 thirds times 1/8 is 2/24 or 1/12 pi. That's sort of a lot of work there at the end. Sorry, that maybe cut off a little bit there. That's 1/12 pi. Okay. It's a lot of work sort of there at the end, just calculating the arithmetic, but the final answer you get is 1/12 pi. Okay. So we're going to stop there for the video. On the homework and the quiz, you'll have a chance to practice these as well as in some other assignments as we move forward.